Let's talk about current and magnetic field. So the most common form of current is just a one-dimensional current. So the way we're going to look at a one-dimensional current for now is some line of charge, in particular some line of linear charge density, let's call it lambda. And then the amount of current depends on how fast the charge is moving, the velocity v. So the current I is just lambda times v. In two dimensions, well, you can have a two-dimensional current in addition to a one-dimensional current, as well as a three-dimensional current. So let's discuss those other cases as well. So a two-dimensional current would be like some kind of sheet, and the sheet is a sheet of charge, and the charge is moving at some velocity v. And so then we say, okay, so there's some surface charge on the surface charge with density sigma. And so then we say there's a surface current. We call it k vector for the surface current, and that's sigma times v, where v is the speed of the charge. Of course, you can imagine what would happen in three dimensions. Let's consider like a tube of charge. And so there's some charge moving here with some velocity v, and this is some volume charge density. And so that might have some charge density rho. And so, of course, we're going to say this is some volume current. And the volume current, the expression will be j vector, and that's equal to rho times v. Another useful way to denote the surface current and the volume current is to look at a little perpendicular bit. So on the surface, you look at a little perpendicular bit of line. And then the surface current K is the differential of the little bit of current di vector divided by dl perpendicular, the perpendicular length. Similarly, in three dimensions, you look at a perpendicular area, dA perpendicular, and then the volume current J is di dA perpendicular. These expressions are really useful when you want to calculate the total amount of current of a surface or volume current. So let's look at an example. Say a uniform volume current J is flowing along a circular wire with some radius A. It might look something like this. And we want to know what is the total current in the wire. So the way we do this is we first look at a little bit of current di, which is J dA perpendicular. And then the total amount of current is just adding this all up over the perpendicular area of the wire. And so A perpendicular, if you remember, dA perpendicular is a little differential area perpendicular to the direction of the current. So here it makes sense to model this in cylindrical coordinates. So dA perpendicular is s ds d phi. And then I total is just a double integral over s and phi. S goes from 0 to a, phi goes from 0 to 2 pi. And so this breaks up into two separate integrals. And we get that the total current is just J times pi a squared. Note that the pi a squared is just the cross-section of the wire. And so really, in this case of a uniform volume current, you're just multiplying the volume current times the cross-section. Let's consider another example where now the volume current depends on the distance from the axis or from the center of the wire, namely J is Ks. We want to calculate what is the total current now. Well, we do the same thing. We're going to add up J times dA perpendicular across the wire. And so now that's Ks, and now dA perpendicular, remember, is s ds d phi. So the integral looks slightly different, but the process is the same. And so we get an s cubed instead of an s squared as before. And so we ultimately get 2 pi over 3 K a cubed for our total amount of current. So that's how we would go from a volume current to the total current in that volume or in that wire. Let's talk a little bit about how we find the magnetic field due to these currents. So if you recall, Coulomb's law says if you have a little bit of charge, dq, and you're interested in the electric field at some point p, you need to know the curly r vector, and then you find a little bit of electric field, dE, by 1 over 4 pi epsilon naught, dq r hat over r squared. There's a similar law for magnetic fields called Biot-Savart's law, and it says if you have a little bit of current, say I dl vector, pointing in this particular direction, and some point p, well, we're still going to be interested in the curly vector r, then the little bit of magnetic field is mu naught over 4 pi, I dl cross r hat over r squared. Notice the cross product in this expression. Mu naught here is a fundamental constant, so it's 4 pi times 10 to the minus 7 newtons per ampere squared. And this is called the permeability of free space, just one of these constants that we have to use. Of course, the total magnetic field is then adding up the little bits of magnetic field from the little bits of wire. And so that will ultimately result in an integral. And this is usually what we call Biot-Savart's law, the full integrated version of Biot-Savart's law. So we have some wire, and there's some little bit of wire along here, call it dl vector, and a current flowing along this wire. Let's draw in some axes. So r prime points from the axes to my current, r points to my point, and curly r points from my current to my point. Then the magnetic field is just the integral of the expression we had above. I dl vector cross r hat over r squared. Of course, the r hat and the cross product makes this difficult to do in practice, but it is something that works just like Coulomb's law. So we can just calculate r hat and r squared and calculate the magnetic field. What about if we had surface or volume currents? What would the expressions look like there? Well, just as in Coulomb's law, you can generalize the magnetic field to surface and volume currents. And it kind of acts as you'd expect. And so instead of I dl, you get k cross r hat and integrate over dA, integrate over the area or the surface. And then for a volume current, then you would get j cross r hat over curly r squared and integrate over the volume d tau. So again, this is an integration over some kind of surface for a surface current and an integration over a volume for a volume current.